Ever try to organize, like, a really messy room?
Yeah. Can't say that I'm the most organized person.
Well, imagine trying to organize a whole universe of mathematical equations and formulas.
It's intimidating.
That's what we're diving into today. This recent research paper is all about bringing order to the chaos, classifying these things called almost-toric systems.
Yes. Almost-Toric systems. These are fascinating because it's like we're establishing a new way to categorize the universe, at least in a mathematical sense. It's like finding a new organizing principle that could impact even physics and engineering.
Okay, I'm already lost.
Okay.
Let's back up. What exactly are almost-toric systems? Can you give me, like, a simple analogy?
Sure. So think of our solar system, right?
Hmm.
Planets orbiting the sun, following these predictable paths. Almost-Toric systems are kind of similar. They deal with mathematical objects that exhibit this really predictable, orderly behavior. We call them integrable systems because we can use math to understand how they'll move and change.
So there's a method to the madness, some rules we can map out.
Yeah, exactly. Now, to be almost-Toric, a system needs a few key things. First, it's got to have this thing called a Hamiltonian.
Sounds complicated.
It's not as scary as it sounds. Think of it like the energy drink of our almost-Toric system, the thing that keeps everything moving.
I like this. Mathematical energy drinks, orderly movement. I'm following along. What else makes a system almost-toric?
They also have these special points, we can call them landmarks, and they're officially known as non-degenerate singular points.
Non-degenerate meaning?
It just means they're well-behaved, no mathematical black holes or anything, and these landmarks are super important. They're like the defining features of the system.
So are these landmarks like the planets in our solar system example?
Exactly. And to tie everything together, we have connected fibers. Imagine these fibers as the gravitational pull between our planets, making sure everything stays connected.
Okay, I'm getting a little lost again. If the landmarks are like planets and the fibers are gravity, what's actually being observed in this almost toric system? Like, what are these mathematical objects in real life?
Good point. We're dealing with mathematical concepts here, so it's easy to get caught up in the analogy. These objects could represent, say, the motion of particles in a fluid, or maybe even the way electrons behave in the magnetic field.
Okay, so it's like a framework for understanding how things interact based on some rules.
Exactly. It helps us understand how these objects, whatever they represent, change and interact within this system.
Gotcha. So we've got our landmarks, our fibers, and our mathematical energy drink. What's next?
Now we got to categorize. We've got to look at these different types of critical points within the systems.
So we're classifying these landmarks we talked about.
Yes, we have focus, elliptic regular, and elliptic points. Don't let the names intimidate you. They're just labels.
It sounds a bit like a sci-fi movie.
Right. But essentially, these labels help us describe the mathematical properties of each landmark. And we can study these landmarks more closely using something called Eliason's linearization theorem.
Sounds complicated.
Think of it like a mathematical magnifying glass that helps us zoom in on these points.
Okay, I'm with you. But why is it so important to classify these points? What's the point?
Because they're the key to understanding and categorizing different almost-Toric systems. By figuring out the types and how they're arranged, mathematicians can start to organize these complex systems. Just like, well, you'd organize a library. You want to group similar books together. We're doing the same thing here, but with math.
Okay, so we've got our landmarks all categorized. It feels like we're building something here, but how do we actually categorize the entire almost-toric systems themselves?
That's where the really cool stuff comes in, how we give each system a unique fingerprint. Mathematicians use things called invariants.
Invariants, like mathematical fingerprints.
Yeah. They're like special characteristics that don't change no matter how you look at the system. And this paper focuses on three main ones. First up, the almost-Toric base.
The almost-toric base, huh? Sounds kind of like the foundation. Can we keep going with our solar system analogy?
Of course. Think of it like a map of our solar system showing where all those planetary landmarks are located.
Instead of continents and oceans, though, we have...
Exactly. The map is divided based on the types of critical points in each area. Remember those focus, elliptic things?
Right.
So we have this process called stratification, basically how we divide up the map represented by B, A, S, each letter for a different type of region.
So I could look at this almost-toric base map and immediately see which areas have a bunch of focus landmarks, which have more elliptic regulars and so on. It's like a zoomed-out view of the whole system.
Yeah, you got it. It gives us that big picture layout of the entire almost-toric system.
Okay, I can see the fingerprint idea now. So what's the second fingerprint we're looking at?
The second one gets into Taylor series.
Uh-oh, sounds complicated again.
It's not too bad. Remember our landmarks?
The focus, and all those.
Each landmark has a unique Taylor series, and this acts like a fingerprint for that specific landmark. It describes how the system acts near that landmark.
So each landmark has its own personality, and the Taylor series is how we write that personality down mathematically.
Perfect analogy. And because math loves to be thorough, there are different types of Taylor series. Relative action, action, and transition Taylor series. Each one shows us something a little different.
Okay, so we've got the overall layout with the almost-toric base, and then the individual landmark personalities with the Taylor series. That's pretty comprehensive, right? Anything else?
One more big one. Imagine two almost-toric systems with basically the same map, and even their landmarks have really similar personalities based on those Taylor series. How do we tell them apart then?
Good point. It's like having identical twins who also have the same taste in music. How do we know they're different people?
That's where our third invariant comes in, the relative twisting index. This one's a little harder to picture, but stick with me. Imagine two pieces of string, same length, but twisted in different ways.
Okay, I think I see where you're going with this.
Even though they've got the same base material, the string itself, our first invariant, maybe even some of the same knots along the way, Taylor series, the way they're twisted around makes them different. That's relative twisting index, how much one system is twisted compared to another.
Wow, that's really cool. So the map, the personality, and the twist. It's like a mathematical detective case. But I have to ask, what's the point of all this classifying? Why do we care so much about these almost-toric systems? What's the big payoff? So we've got the map, the personality, and even the twist figured out. Sounds like we've got all the tools we need to classify these mathematical mysteries.
And that's what makes this research so groundbreaking. It gives us a theorem, a way to definitively categorize these almost-toric systems, at least in 4 dimensions, using these 3 invariants.
Hold on, so just by analyzing the almost-toric base, figuring out those unique Taylor series, and factoring in the twist, we can classify any of these systems.
Exactly. It's like having a universal filing system for these complex mathematical objects.
That's incredible. But why go through all this trouble? What's the practical use of all this classifying?
Well, think about predicting the weather. Imagine if we could use these systems to understand the way air currents move in the atmosphere. Or how about designing better superconductors by studying electron behavior? The possibilities are huge.
Wow, that's pretty amazing. So by understanding these systems, we could be looking at a whole new world of technology and scientific advancement.
Exactly. And the paper even hints at more to discover. Apparently, there might be a link between almost-toric systems and something called semitoric systems.
Semitoric systems, what are those?
That's the exciting part. They're even more complex, and we don't know as much about them yet. It's like we've found a hidden door in our library leading to a whole new section of knowledge.
It sounds like this deep dive was just the tip of the iceberg. We've journeyed from organizing mathematical equations to potentially revolutionizing our understanding of the universe. It makes you wonder, what other mysteries are hidden within these systems? What new discoveries await those who dare to explore the world of almost-toric systems further? Keep those minds curious, everyone.
Ever feel like the world is just a bunch of complex systems and we're just barely scratching the surface of understanding them?
Yeah, definitely makes you feel kind of small, right?
Well, get ready to decode one of them with me. Today we're taking a deep dive into almost-toric systems.
Oh, cool.
Now, before you hit that 30-second skip button, I promise this isn't just some abstract math lesson.
Definitely not.
We're talking about tools to understand the systems that shape our lives, from planetary motion to maybe even the stock market.
It's going to be a wild ride.
To get us started, let's imagine a perfectly balanced mobile, the kind you hang above a crib.
Okay, I can picture that.
Each piece moves in a predictable way, influencing all the others. That's an example of an integrable system.
Right.
Mathematicians love to organize these systems, much like we try and often fail to organize that chaotic junk drawer.
Well, and you know what's funny is that mathematicians have already tackled the toric and semitoric systems.
Yeah.
Those are like the neatly labeled boxes in your analogy.
Right.
But almost-toric systems are like that one box shoved in the back, full of tangled wires and who knows what.
Oh, no.
We're only just beginning to unpack it.
Okay, almost-toric it is. So, no more mystery boxes. Let's break it down. What are the key elements of an almost-toric system?
Picture a map. But instead of countries, it represents all the possible states of our system.
Okay,
This map is our base.
got it.
Now imagine this map has different textures. Smooth in some places, rough in others.
Okay, I think I'm following.
This is the stratification. Different regions behave differently because the system's underlying rules change.
So if the base is like a map of the system's possibilities, what makes one region smooth and another rough?
Think of it this way. In a smooth region, small changes to the system only lead to small, predictable outcomes.
Okay.
But in a rough region, even a tiny change can cascade into something totally different.
Yeah, like a butterfly effect kind of thing.
Exactly like a tiny tremor causing an avalanche. Understanding these regions and their boundaries is key to predicting how the system might behave.
Okay, I'm starting to see how this connects to understanding real-world complexity.
It's all connected.
What's next on our Almost-Toric toolkit?
Next up, we've got Taylor series invariants.
Okay.
Think of them like unique fingerprints for each point on our map.
So more than just a visual map, we're talking about a system with measurable, unique identifiers for each point.
Exactly.
But how do these fingerprints actually work?
Imagine zooming in on a single point on our map.
Okay.
The Taylor series gives us a way to describe that point's behavior over time.
Like a mathematical time lapse?
Yeah, kind of. And because each point has its own unique Taylor series, we get this incredibly detailed picture of how the entire system evolves.
This is giving me a whole new appreciation for the phrase mapping out the possibilities. So we've got our map, the stratified base, and these unique Taylor series fingerprints. What else is there?
Here's where it gets even more interesting. We have these things called twisting indices. Now, hold on to your hats because this is where our nice, neat map might actually feel like a Mobius strip.
A Mobius strip. Okay. You've officially piqued my curiosity. What exactly do these twisting indices tell us about an almost-toric system?
Well, they basically, they measure how much our system is, well, twisted.
Okay.
Think of two systems, both with the same base map and even the same Taylor series fingerprints.
Okay.
They seem identical, right?
Right.
But the twisting indices can be totally different, and that changes everything.
So even if two systems look identical on the surface, a hidden twist can completely change their behavior?
Exactly.
This feels like one of those aha moments, like realizing why two seemingly similar events can lead to vastly different outcomes.
Precisely. It's like having two identical recipes, but one includes a pinch of a secret ingredient that transforms the entire dish.
Right.
And that's what makes understanding these twists so crucial.
This is making me think about how we often try to analyze complex systems based purely on observable factors, like in economics.
Yeah.
But what if we're missing the twist that's driving the real change?
That's a great point, and it highlights why this mathematical framework is so powerful.
Okay.
By understanding the twisting indices, we gain a deeper understanding of the underlying structure of a system and how it might behave, even if some aspects seem counterintuitive at first glance.
So to be clear, are we talking about a single twist for the entire system, or can different parts of the system have different twists?
That's where it gets even wilder. We're not just talking about one global twist.
Okay.
Different regions on our map can have different twisting indices.
Okay.
So you might have a region with a tight twist, bordering another region with a gentle twist, which creates all sorts of interesting dynamics.
Wow. Okay. So we're not just mapping a static system here. We're talking about a system with different regions behaving differently, interacting with each other, all influenced by these hidden twists.
It gets complicated.
It's like trying to predict the weather patterns on a planet with constantly shifting continents.
Yeah,
It's a lot to wrap your head around.
it is a lot. But that's also what makes this field of study so fascinating.
Right. And it's important to remember that we're just starting to scratch the surface of what almost-Toric systems can reveal about the world around us.
You said it. So before we dive into the why should we care portion of all this, is there anything else we need to know about these twisting indices to fully grasp their significance?
Well, I have to say, this idea of twisting indices within a system is really making me rethink how I view seemingly predictable things.
It's one of those concepts that once you grasp it, you start to see its relevance everywhere. Think about it. We make decisions based on what we think we know about a situation, but what about the hidden twists we might be missing?
Exactly. It's like you could have two companies with similar business models, similar market share, but one has a hidden twist. Maybe it's their company culture or a unique approach to supply chain management. And that twist gives them a competitive edge that's not immediately obvious.
And that's where the real-world application of this mathematical framework comes in. It's not just about crunching numbers. It's about developing a deeper understanding of how complex systems work, what factors, both visible and hidden, are driving their behavior.
So in essence, we're talking about a new lens through which to view complexity, a lens that helps us make sense of those unexpected outcomes, those moments where you say, wait, how did that happen?
Precisely. And while we might not always be able to calculate the exact twisting indices of every system we encounter, after all, not everything can be neatly quantified. The very act of looking for those hidden factors can be incredibly valuable.
This has been an incredible deep dive, and you've given us a lot to ponder. If our listeners could take away just one key insight from our exploration of almost-Toric systems, what would you say it should be?
That's a great question. I think the biggest takeaway is this. Even seemingly identical systems can have hidden differences, those twists that shape their behavior in profound ways. It's a reminder to look beyond the surface, to consider multiple perspectives, and to expect the unexpected.
So the next time we encounter a complex situation, whether it's a personal dilemma, a scientific puzzle, or even just trying to understand the latest market trend, remember those almost-Toric lessons.
Absolutely. Look for the hidden twists, the subtle differences that can make all the difference. You might be surprised by what you discover.
I love that. This has been a fascinating journey into the world of almost-Toric systems. A huge thank you to you for illuminating this surprisingly relevant area of mathematics.
It's been my pleasure. Always happy to delve into the intricacies of complex systems.
And to our listeners, thank you for joining us on the deep dive. We'll catch you next time for another exploration into the depths of knowledge.
Ever get fascinated by something that walks this fine line between order and chaos? Like, think about a spinning top.
Okay.
You can generally predict how it'll move, but there's always that wobble, the little bit of unpredictability.
Right.
Turns out there's this whole area of math dedicated to systems like this,
Yeah.
and you're about to become an expert on them.
Okay.
At least for the next few minutes.
Yeah.
We're diving into the world of almost-Toric systems. A mouthful. Oh, I know, but trust me, it's much cooler than it sounds.
All right.
We've got a brand new research paper to guide us.
Okay.
And it's basically cracked the code on how to classify these systems.
Right.
Like finding a way to organize all the different dances a spinning top can do.
What's so captivating about this area of math is that it's like detective work. Mathematicians are trying to find patterns in these hidden structures in systems that seem almost unpredictable.
Right.
And with almost-Toric systems, they've really had their work cut out for them.
Right. It's like they've stumbled onto a crime scene, but instead of footprints and DNA, they're dealing with equations and geometric shapes.
Yeah.
So to set the stage, let's talk about what we mean by predictable in this context.
Sure.
We're dealing with what mathematicians call integrable systems.
Exactly. Imagine a pendulum swinging back and forth. It's
Yeah.
very regular, very predictable, right?
Yeah.
That's like a simple example of an integrable system.
Okay.
And mathematicians, being mathematicians, have developed ways to describe these systems mathematically, sort of like creating a blueprint for their behavior.
Okay, so we've got our predictable systems, like our trusty pendulum,
Right.
but where do these toric and semitoric systems fit in?
You're telling me?
Those are words you don't hear every day.
Yeah, you don't hear those every day.
Not usually.
Think of toric systems as the perfectly predictable systems,
Okay.
even more so than our pendulum. They're the easiest to classify. Think of them as the starting point. Then you have semitoric systems, which are a step up in complexity.
Okay.
They're still predictable, but with a bit more nuance,
Oh.
kind of like that spinning top we were talking about.
Right.
A bit more wobble, a bit more intrigue.
So naturally, mathematicians being the curious bunch, they decided to push the boundaries even further.
Yeah.
They asked themselves, what happens when we explore systems that are almost predictable, almost toric?
Right.
And bam, almost toric systems were born.
There you go.
But how do you even begin to make sense of something that's almost something else?
That's the million-dollar question.
Right.
What makes almost-Toric systems so fascinating is that they have these specific points where their behavior changes in really interesting ways.
Okay.
Kind of like how a spinning top might suddenly change its axis of rotation. Mathematicians call these singular points.
Okay.
And understanding these points is key to unraveling the mysteries of these systems.
Okay, so we need to pay close attention to those singular points. But we also need to remember that we're dealing with systems that still have some level of predictability, right?
Right.
It's not complete chaos.
They're not completely random.
Okay.
They have rules, but the rules are just a little more complex, a little more subtle.
Okay.
And to make things a bit easier to visualize, we'll focus on four-dimensional systems for this deep dive.
4 dimensions now. You're just showing off. But in all seriousness, why 4 dimensions?
It's a sweet spot, really.
Okay.
4 dimensions give us enough complexity to explore the interesting behaviors of almost-toric systems without getting too lost in the mathematical weeds.
Okay.
So think of it like this.
Okay.
2 dimensions would be too simple, like trying to understand a spinning top by just looking at its shadow.
Okay.
And more than 4 dimensions, well, let's just say our human brains might have a hard time wrapping themselves around that.
That's fair. I'm all for keeping things as comprehensible as possible.
Yeah.
So we've got these 4-dimensional systems with their unique singular points. But how do we start classifying them, organizing them in a way that makes sense?
Yeah.
It's not like we can just line them up and say, well, this one looks a bit more almost toric than that one.
Exactly.
Yeah.
You're right. We need a more systematic approach.
Okay.
And that's where this new research comes in.
Okay.
It basically gives us a set of tools, a kind of mathematical toolkit
Okay.
to identify and classify these systems based on their unique properties.
Okay. I'm intrigued. Let's break open this toolkit and see what we're working with.
Okay.
What are the key components that help mathematicians tell one almost toric system from another?
Think of it like this. Imagine you're trying to classify different types of bicycles.
Okay.
You might start with the frame, right?
Right.
That's kind of like what mathematicians do with almost-toric systems.
Okay.
They use something called a base,
Okay.
which acts like a map of the system's overall structure.
Okay, so the base is like the bicycle frame.
Right.
It gives us the basic shape.
Exactly.
But bicycles have all sorts of other components.
Yeah.
Wheels, gears, handlebars.
Right.
What are the mathematical equivalents of those in an almost toric system?
Great question. This is where those singular points we talked about earlier come back into play.
Okay.
Remember, those are the points where the system's behavior gets really interesting.
Right.
Well, each singular point actually has a unique mathematical description attached to it, like a fingerprint.
Okay.
And these descriptions are encoded in something called a Taylor series.
Hold on, Taylor series.
Yeah.
Like from calculus class.
Yeah.
Those infinite sums of terms.
You got it.
I'm getting flashbacks to late night study sessions.
Laughs. They're one of those mathematical tools that pop up everywhere.
Right.
And in this case, they help mathematicians capture the subtle differences between systems that might look very similar on the surface.
Right.
It's like how 2 bicycles might have the same basic frame but different gear ratios,
Right.
which would make them behave very differently on a steep hill.
Yeah. Okay. I'm starting to see how these Taylor series add another layer of detail to our understanding of these systems.
Yeah.
But I have a feeling we're not done yet.
Right.
What about those twisting indices you mentioned earlier?
Yeah.
Those sound even more intriguing.
They're definitely one of the more intriguing aspects of almost-toric systems.
Right. And a bit mysterious, if I'm being honest.
Imagine you have a rubber band and you twist it.
Okay.
The number of twists you put on that rubber band changes its overall shape, how it behaves, right?
Right.
Twisting indices capture a similar idea for these mathematical systems.
Okay.
They tell us how much the system is twisting and turning around those singular points.
So it's not just about the location of those singular points on our map,
Right.
but also how much the system is, well, twisting around them.
Exactly. And just like with the rubber band, even a small twist can dramatically change how the system behaves overall.
Okay. This is starting to make my head spin a bit, but in a good way.
Uh-huh.
We've got the base, the Taylor series, and these twisting indices. It's like we're building this incredibly detailed fingerprint for each almost toric system.
Yeah.
But how do we know that these 3 things are enough to uniquely identify a system? How do we know that we haven't missed some other crucial piece of information?
That's where the real elegance of this research comes in.
Okay.
The mathematicians behind this paper were able to prove that knowing just these 3 things,
Okay.
the Taylor series invariants and the twisting indices,
Yep.
is enough to uniquely identify a 4-dimensional almost-toric system.
Wow.
It's like finding the magic key that unlocks a treasure chest full of mathematical knowledge.
That's incredible. It's like having a complete set of blueprints Not just for one type of bicycle, but for every possible bicycle that could ever exist.
That's a great way to put it. This classification is a major achievement.
Yeah.
It's like creating a catalog for a vast library of these systems,
Okay.
making it possible to understand and compare them in ways that weren't possible before.
It's like finally being able to organize that chaotic drawer in your kitchen where you keep all the miscellaneous gadgets.
Yes, exactly.
But in this case, instead of potato peelers and bottle openers, we're talking about complex mathematical objects.
Right. And you know what happens when you finally get things organized?
What?
You can start to see patterns, make connections, and ask deeper questions.
So what are some of those deeper questions? What mysteries are mathematicians hoping to unravel now that they have this new classification system for almost-Toric systems? It's like we've just finished this giant jigsaw puzzle, and now we can finally step back and appreciate the whole picture.
Right.
What new insights can we glean from this newfound understanding of almost-Toric systems?
One of the most exciting aspects of any mathematical breakthrough is that it often opens up more questions than it answers. It's like reaching the top of one mountain only to discover a whole range of uncharted peaks in the distance.
Right.
With this classification system in hand, mathematicians are already setting their sights on new horizons.
So where do they go from here? What are some of the unexplored territories in the world of almost-Toric systems?
Well, for one, this research focused specifically on four-dimensional systems.
Okay.
That begs the question.
Yeah.
Can we extend these classification tools to higher dimensions?
Okay.
5 dimensions,
Right.
10 dimensions. It's a tantalizing challenge that has mathematicians buzzing with excitement.
It's like we've just dipped our toes into a vast ocean of mathematical possibilities.
Yeah.
But dimensions aside,
Right.
I'm always curious about the practical implications.
Sure.
Does this new understanding of almost-Toric systems have any applications in other fields?
That's the million-dollar question, isn't it?
Right.
And while it's still early days, there's a sense of anticipation in the air.
Okay.
Many fields grapple with systems that exhibit the same blend of predictability and complexity that we see in almost-Toric systems.
You're right. Think about weather patterns,
Yeah.
financial markets, or even the behavior of crowds. They all have these elements of predictability, but also this element of inherent chaos.
Precisely. And while this classification system won't magically predict tomorrow's stock prices or next week's weather,
Right.
it provides a powerful new framework for thinking about complex systems in general.
Okay.
It's like having a new set of lenses that allow us to see the world in a different light, revealing hidden patterns and connections that we couldn't perceive before.
This is what I find so fascinating about mathematics.
Yeah.
It's a field driven by pure intellectual curiosity, a quest to understand the fundamental building blocks of our universe. But then, often unexpectedly, these abstract explorations lead to insights that have the potential to reshape our understanding of the world around us.
It's like those early astronomers who meticulously charted the movements of the stars driven by this thirst for knowledge.
Right.
Little did they know that their discoveries would lay the foundation for navigation timekeeping and our entire understanding of the cosmos.
What a fantastic analogy. And that's what makes this deep dive into almost-Toric systems so exhilarating.
Right.
We've witnessed the creation of a new kind of map, a mathematical map, that has the potential to guide us to new discoveries in fields as diverse as physics, economics, and even social sciences.
And the best part is this is just the beginning.
Right.
As mathematicians continue to explore and refine this new classification system, who knows what hidden treasures they'll uncover. One thing's for sure.
What's that?
The future of almost-Toric systems and the insights they hold is brimming with possibility.
It's enough to make your head spin, but in a good way, of course. It's a good reminder that even in the most abstract realms of mathematics, there's a sense of wonder and beauty waiting to be discovered. And who knows? Perhaps these discoveries will one day reshape our understanding of the world in profound and unexpected ways. Until then, keep exploring, keep asking questions, and never lose your sense of curiosity. Welcome to the Deep Dive. Today, we're diving into the fascinating world of almost-Toric systems. Now, based on the research excerpts you shared with us, you're particularly interested in how mathematicians actually classify these systems, which, let me tell you, is no easy feat.
It really is like trying to organize well. Imagine a library, but it has infinite shelves, and all the books are written in a language you're only just starting to grasp.
Yeah. That's a great analogy. So before we get into like the really complex stuff about classification, maybe you can give us a high-level overview of what almost-toric systems actually are. I mean, we saw the terms toric and semitoric in the research too. How do those all connect?
Okay, so imagine for a second that these systems are like maps, but instead of guiding you through physical space, they chart how different elements interact within a system. So think about toric systems, the most straightforward type. It'd be like navigating a perfectly gridded city, predictable, easy to find your way around. Now, semitoric systems, those are a bit like adding roundabouts to that city. Maybe some winding roads, a touch more complex, but still manageable. But almost-toric systems, those are like venturing into a city designed by M.C. Escher, full of fascinating loops, twists, unexpected connections everywhere.
Okay, wow. I can already see why just wrapping your head around these systems is a challenge, let alone classifying them. But it's important, right? Like, it's about imposing some kind of order on something that seems chaotic.
Exactly. You hit the nail on the head. And it's not just about satisfying a mathematician's love of order either. These systems, they aren't merely abstract concepts. They have real-world applications in physics, engineering, anywhere we try to model complex systems, especially ones with repeating patterns.
So like how energy flows in a system.
Exactly. Or even think about the fabric of space-time itself. By classifying these almost torrendous systems, we're essentially developing a toolkit, you see. A powerful toolkit to analyze and predict how these systems behave.
So it's like instead of just having a jumbled toolbox, where you're just rummaging around hoping you find the right tool.
You get it.
We're creating a well-organized one where everything has its place. Now, the research paper you shared, it breaks down this how of classification into three main parts. Let's start with the base. That seems pretty foundational, wouldn't you say?
It is. It's like the system's underlying structure. Think of it, again, like a map. But instead of countries, it has regions. And each region represents a different type of point. And just like a map has, landmarks, this base has what we call special points. These are the focus points.
Focus points, got it.
And they're crucial, these points, because they show us where the system's behavior gets really interesting, where things might deviate from what we normally expect.
So not just any point on the map, but these specific points of interest.
Exactly.
And the research mentioned something about their arrangement being important too, something about cut rays.
Ah, yes. You're right. The way these focus points are arranged, well, it adds a whole other layer of complexity. And those cut rays you mentioned, they're key to understanding how these points all relate to one another. Imagine, if you will, drawing lines or rays out from each of these focus points. They slice through the map, these rays. And the way they intersect or don't intersect, well, that gives us valuable information about the system's overall structure and how it behaves.
Okay, so we've got this base, our map, with its special focus points. And these cut rays, they give us even more information. What comes next?
Well, we were saying how each focus point is like a point of interest, right? Well, each of these points also has its own unique fingerprint, so to speak. And in this world, those fingerprints are what we call Taylor series invariants.
Hold on. Taylor series invariants. Now we're really getting into some higher level math here. You have to break that down for us.
You're right. It sounds a bit intimidating. But it's a really cool concept once you grasp it. Think about it this way. In math, we often use what are called series, basically infinite sums of terms, to represent functions. A Taylor series is just a specific type of series, one that's really good at approximating how a function behaves, but, and here's the important part, near a specific point.
Okay, so we're zooming in on the behavior around those focus points using these Taylor series.
Exactly, and here's the really cool part. Each focus point, it gets its own unique Taylor series. It's like its own fingerprint, and that fingerprint captures how the system behaves, specifically in the vicinity of that point.
So these fingerprints, or Taylor series invariants as they're formally called, they help us classify and differentiate between these almost-toric systems.
You got it. Powerful stuff, these Taylor series invariants.
Yeah. So we've got our base with its special focus points. We've got the cut rays telling us more about how they're arranged. And now we've got these unique fingerprints, these Taylor series invariants. It's like we're building a super detailed profile for each system. But there's one piece of the puzzle left right. The relative twisting index. That's right. We still need to untangle this whole relative twisting index thing. And I got to say, this one, it sounds kind of like, I don't know, a figure skating move gone wrong or something.
I can see that.
So what exactly are we twisting here? And why is it so important for understanding these systems?
Okay, so picture this. You could have two almost-Toric systems, and at first glance, they look practically identical. Same base, even similar Taylor series invariants, but there'd still be these subtle differences in their structure. It'd be like, imagine comparing two tapestries. They have the same overall pattern, right? But when you look closer at the weave itself, you start to notice these tiny variations. That's what the relative twisting index helps us do. It teases out those subtle but crucial distinctions.
Okay, so it's all about those little nuances, the details that really matter. But how does this twisting actually show up, in the math that describes these systems?
Right, good question. Without getting too deep into the weeds here, imagine you're taking a loop around one of those focus points on our map. As you travel along that loop, the system's behavior might twist or rotate in a specific way.
Got it, like it's following some kind of curved path.
Yeah, you could think of it that way. Now let's say you take a similar loop around the corresponding focus point, but in that other seemingly identical system.
And that's where we might see a difference in how the twisting happens.
You got it. The relative twisting index. It basically measures how the twisting in one system compares to the twisting in the other. It puts a number to those subtle but crucial distinctions.
Okay, so going back to our tapestry analogy, it's like the overall patterns might look the same, but the relative twisting index allows us to see how the threads are woven together differently.
Exactly. It reveals those hidden complexities.
This is great. So just to recap everything we've talked about so far, we've got the base, the foundation of the system. We have the Taylor series invariants, those unique fingerprints for each focus point. And finally, we have the relative twisting index, which captures those subtle but important differences in twisting. It's like we're using a set of increasingly powerful lenses, each one revealing a whole new layer of complexity within these systems. But I think it's time we step back for a second. We've been really deep in the weeds of the how of classification. But what does all this actually mean for someone who's not, a mathematician who spends all their time with these formulas? Why should we care about all this?
That's such an important question. It's easy to get caught up in the technical details, right? But we have to remember, these systems, even though they're rooted in abstract math, they have really significant implications. Remember, we were talking about how they pop up in physics, engineering, even the study of how things change over time in nature.
Right, like they're the hidden mathematical structure behind all these complex things.
You got it. And here's the thing. By classifying these almost-toric systems, mathematicians are basically developing a new language, a more powerful, more precise language, to describe and analyze those complex phenomena we were just talking about.
So it's about going beyond just observing these systems and getting to a point where we can actually predict how they'll behave.
Exactly.
And even understand how even small changes in one part of the system can end up affecting the whole thing.
Precisely. And that has huge implications for scientific progress.
Okay.
For example, in physics, these systems are being used to model how quantum systems behave.
Okay, so now we're talking about potentially unlocking the secrets of the universe.
Well, maybe not the entire universe, but it could have a huge impact on everything from developing entirely new materials to understanding the fundamental nature of reality itself.
Wow, that's incredible. We started with classifying math systems, and now we're talking about the fabric of reality. This is a real deep dive today. But before we get too carried away with quantum physics, you mentioned other fields where this classification system is important. What about engineering? I'm really curious to hear how this abstract mathematical framework actually plays out, in tangible, real-world applications in engineering.
Yeah, absolutely. So how does all of this apply to engineering then?
Well, imagine you're an engineer, right?
Yeah.
And you're designing this really complex system with all these different parts that have to work together perfectly, like a power grid, for example, or a huge telecommunications network. These kinds of systems, they often have these patterns and behaviors, and you can actually model them using almost-Toric systems.
Wow, really? So instead of relying on, trial and error,
right,
or just using simplified models that don't really capture everything,
exactly,
engineers can actually use this classification system to really get a deep understanding of how these systems work. Yes. And it's not just about understanding, it's about getting a more precise understanding.
Right, because the more precise you are, the better you can design these systems.
Yeah.
And you can even start to predict how they'll behave.
Right. Exactly. This could lead to, well, think about it, more efficient designs, better predictions of, how the system will respond in different situations, and ultimately just more robust solutions to the engineering challenges. For example, remember that relative twisting index we were talking about?
Oh yeah, the one that helps us see those subtle differences.
Yes, that one. Understanding those subtle twists, it could be the key for engineers to anticipate and prevent potential issues in a system. Like imagine being able to head off instabilities before they even happen.
That's incredible. It's amazing how something that seems so abstract, like so grounded in pure mathematics,
Yeah.
can have such a concrete impact on the technology we use every single day.
It really speaks to the power of mathematics. It's like this language that helps us understand the universe from the biggest, most complex things down to the tiniest details. But speaking of big and complex, this research we've been talking about, it mainly focuses on classifying these systems in 4 dimensions.
Okay, 4 dimensions, right?
But have you ever wondered what happens when you start exploring higher dimensions?
Now that's getting a little mind-bending. So we're talking about like spaces with more than just the 3 spatial dimensions that we experience.
Exactly.
Honestly, I'm already having trouble picturing it.
It's definitely a wild ride for the imagination. Try to imagine for a second what the shadow of a 4-dimensional object would look like.
Okay, I'm trying.
Now try to picture the shadow of that shadow, but in 5 dimensions.
Yeah, my brain just went into overdrive.
It's not easy. But here's the thing. It's not just about these abstract visualizations, these higher dimensional, almost toric systems. They could have some really profound implications for how we understand the universe works.
So basically, we're in uncharted territory here, both in the math itself and in terms of what these systems might even represent in the real world.
Exactly. It's a whole new frontier.
So what are some of the biggest challenges then for mathematicians trying to explore these higher dimensional spaces?
Well, the biggest one is probably just the sheer complexity. As you add more dimensions, the number of possibilities just explodes. And a lot of the tools and techniques, the ones we use for those lower dimensions, well, they often need to be like completely reworked.
Oh, wow. So you're almost having to invent new math just to tackle these problems.
In a way, yeah. But that's also what makes it so exciting. Because with that complexity comes a whole universe of possibilities.
Right. Who knows what you might find out there?
Exactly. There could be these incredible mathematical structures just waiting to be discovered in those higher dimensions.
That's so cool. It really makes you realize how much we still don't know.
It's humbling, isn't it?
And it seems like even though classifying these Almost-Toric systems might seem kind of like a niche area of math,
Right. It might seem that way at first.
it could actually be a key to unlocking some of these bigger mysteries about the universe.
Absolutely. It's like we're building this staircase into the unknown. And every step we take, well, it just opens up these amazing new views, new perspectives on how everything fits together.
That's a great way to put it. And on that note, I think it's time to wrap up our deep dive into the incredible world of Almost-Toric systems. We hope you've enjoyed exploring these concepts with us and maybe even come away with a little bit of a sense of wonder about the hidden mathematical structures that shape everything around us. And who knows, maybe this has even inspired you to do a little exploring of your own. As always, if you have any questions or if there's anything you'd like to dive deeper into, please don't hesitate to reach out to us. We love hearing from you. Until next time, keep those minds curious and keep exploring. Hey everyone, buckle up because we're about to wrangle with a paper titled A Note on the Symplectic Classification of Almost-Toric Systems.
Yeah, that's a bit of a mouthful, isn't it?
It definitely sounds like we're in for a wild ride. So, tell me, what's the big deal with this paper? What's it all about?
Well, imagine trying to solve a jigsaw puzzle, but the pieces are all mixed up and you don't even have the box to know what the picture's supposed to be.
Oh, that's frustrating just to think about.
Right. Well, that's kind of the situation mathematicians found themselves in with these things called almost-toric systems. They're these intricate mathematical systems that pop up in different fields, and this paper is trying to make sense of them to find a way to classify them.
Okay, so it's like they're creating order out of chaos.
Ah.
But before we get into the organizing, let's back up a bit. What exactly are almost-toric systems?
You know how planets orbit a star in a predictable way? Like their movements are governed by certain rules, certain quantities that stay constant.
Yeah, like their energy level, right?
Exactly. That's what we call an integrable system.
Got it. Predictable behavior. But this paper isn't about planets, is it?
Not quite. See, to get to almost toric, we got to talk about toric and semitoric systems first. It's like levels in a game. Toric systems, they're the easiest, perfectly fitting puzzle pieces. Semitoric systems, a bit more complex, some parts fit, others don't.
Okay, so each level gets trickier. So where do these almost toric systems fall on this scale?
They're the boss level. They're the most complex with these weird focus points that make them super hard to grasp.
Focus points. Okay, that sounds intense. So this paper wants to bring order to these chaotic, almost toric systems, but how?
They're trying to classify these almost toric systems based on their essential properties, or what we call symplectic equivalence.
Symplectic? Whoa. Okay, hold on. You're going to have to break that one down for me.
Essentially, it's about figuring out what truly makes each system unique, even if they might look different at first glance. Imagine a square, right? You can rotate it, but it's still a square, just from a different angle.
So symplectic equivalence is like seeing through those different viewpoints to the core of the system.
Exactly. It's about identifying the underlying structure, the mathematical equivalent of a system's DNA.
I like that. Finding their mathematical DNA. So how does the paper go about doing that?
They break it down like a recipe. The authors identify 3 key ingredients, or invariants, that together act as a unique fingerprint for any almost toric system.
Okay, I'm definitely intrigued. What are these magical ingredients?
They're called the base, the Taylor series invariants, and the relative twisting index.
Those sound a little intimidating. Can we break those down a bit more? Let's start with the base. What's so special about it?
Think of the base as the system's blueprint. Like, just as the foundation of a building determines its shape, the base of an almost toric system dictates its overall structure. Except these bases have these quirks, these special points we call nodes, that make them unique and quite hard to study.
So the base is like the system's overall layout, but with a few twists and turns along the way. What about these Taylor series invariants? That sounds vaguely familiar from calculus class, but...
You're not wrong, it does come from calculus. But don't worry, you won't need to dig out your old textbooks. Think of Taylor series as a mathematical microscope, allowing us to zoom in and analyze the system's behavior near those tricky focus points we talked about earlier.
Ah, so if the base is the blueprint, then the Taylor series is the magnifying glass we use to see the fine print.
Exactly. And lastly, we have the relative twisting index.
Okay, what does that one tell us?
Imagine you have 2 ropes that look identical, but you twist them relative to each other. The relative twisting index measures how much twist there is between 2 almost-toric systems.
So it's like those optical illusions where 2 things seem the same, but something's just dot off. You might not notice the twist right away, but it makes a difference.
That's a great analogy. Even if 2 systems have the same base and Taylor series, this twist can make them behave in completely different ways. So this index helps us capture those subtle yet really important differences.
So we've got these 3 ingredients, base, Taylor series, and twisting index, that help us unlock the secrets of almost-toric systems. But I got to ask, what's the point of classifying them like this? Why does it matter if one system's a bit more twisted than another, or if their bases have different quirks?
That's the heart of it all, isn't it? We could easily get lost in the weeds, the math, but it's crucial to zoom out and see the forest for the trees.
So what's the bigger picture here? Why does this research really matter?
Well, think of it this way. For mathematicians, this paper is like discovering a brand new toolbox. These invariants we've been talking about, they're the tools that let them examine these systems in ways they never could before. It's about opening up new avenues to answer questions that were previously out of reach.
So it's not just about putting labels on things. It's about understanding these systems on a much deeper level and uncovering new possibilities.
Exactly. And remember how we talked about those potential applications in physics? Just imagine being able to predict how these complex systems behave with way more accuracy than we ever thought possible. That could change everything.
Like what? Give me an example. How could this impact the real world?
Well, take something like designing more efficient solar panels, for instance, or developing entirely new medical treatments. The potential impact is huge.
Wow, we really could be talking about some world-changing stuff here. This is incredible.
And this is just the beginning. The paper mainly focuses on 4-dimensional systems, but what if we could take this classification system even further to higher dimensions?
It's like we've only explored one tiny island in a vast archipelago. There's so much more out there to discover.
Precisely. And who knows what applications we might find. This could be revolutionary for fields like computer science, economics, even art. The possibilities are truly endless.
That's what I love about these deep dives. You never know what mind-blowing connections we'll stumble upon. Okay, so we've gone from this jumbled mess of almost toric systems to a well-organized library, all thanks to this classification system. Pretty cool. But let's talk practical applications. Why should anyone outside of, theoretical math care about these fingerprints and twisting indexes and all that?
It's a valid question, for sure. It's easy to get caught up in the beauty of the math itself, but the real magic happens when we can connect it to the bigger picture, right?
Exactly. What's the bigger picture here? What kind of impact could this research have down the line?
Well, for mathematicians, it's like they've been handed a brand new set of tools. They can use these invariants to study almost-toric systems in ways that they could only dream of before.
So it's not just about categorizing anymore. It's about pushing the boundaries of what we know.
Absolutely. And remember those applications in physics we were talking about earlier? Imagine if we could predict how these complex systems behave with incredible accuracy.
That would be huge.
Right. It could revolutionize so many fields. Think about designing super efficient solar panels or even developing entirely new medical treatments. The potential is mind-blowing.
Wow. We really could be talking about changing the world with this.
And who knows what other fields might benefit? Computer science, economics, even art. This classification system could be a game changer.
It's amazing to think that something as, abstract as classifying mathematical systems could have such a tangible impact on the real world.
It really shows you the power of fundamental research. You never know where it might lead, and that's what makes this paper so exciting, It's not just about finding all the answers. It's about asking the right questions, pushing the boundaries of human understanding. Who knows what we'll discover next?
Well said. It's definitely time to wrap up our deep dive into the world of almost Molyneuxic systems for today. We've covered a lot of ground, from those tricky focus points to the mind-blowing implications of this research. But before we go, I want to leave you with one final thought.
I'm all ears.
We've been talking about how this classification system helps us analyze almost toric systems that already exist, right?
Right.
But what if we could take it a step further? Could we use this knowledge to actually design new systems? Systems with specific properties and behaviors tailored to our needs.
Whoa. Now that is a fascinating question. It would be like, instead of just understanding how a car engine works, we learn to build a brand new engine from scratch, one that's perfectly fine-tuned for maximum performance.
Exactly. Imagine the possibilities. We could engineer these systems to solve really specific problems, create entirely new materials, or even develop completely new forms of art and music.
It's an incredible thought. I'm sure this idea alone will spark countless research projects in the years to come.
I have no doubt about that. And for our listeners, if you're feeling particularly adventurous today, we'll be sure to link the paper and some other cool resources in the show notes.
It's been a pleasure exploring this fascinating world with you today.
The pleasure was all ours. Until next time, keep those brains buzzing, and remember, even the most complex ideas can be broken down step by step.